Better.
All right. Okay, so here's yet another way to write the power system. So let's just take a look at this guy. So we kind of realize that, all right, so this is, if you were working a big hydroelectric dam, you'd be able to measure pressure at the bottom of the dam. And so do put these equations in and say this is how our little micro hydro system differs physically from a hydroelectric dam. Because if you're a hydroelectric, you say, what's the pressure? And obviously the reason the dam is so high is you can have a lot of pressure on one side and atmospheric pressure on the other. And then you also want to have a high flow rate. So we're going to step back or step sideways or step in some direction and look at this other definition. So I'm going to say P, and what the heck, I'll just go ahead and write hydro. But this is going to be the same for hydro or for wind. You have some fluid moving through a system. And I think this is where I just kind of confused myself a little bit earlier. I was writing down Q as the mass flow rate. It's actually the volumetric flow rate. Right here, what we're looking at is the mass flow rate. So let's go ahead and do our dimensional analysis really quick. That funny little dot actually means with respect to time. It's the time derivative. So what we're looking at is the mass, how much mass is flowing through per unit time. That's where I got the two theories confused. We're back on track now. And here is length squared over time squared minus length squared over time squared. And again, it's the units. This is kind of a funny way of writing it. We'll go back and we'll say that we've got mass times length squared over time cubed. I'm just kind of doing the units. If that's confusing right there, length, you might say, oh, length squared minus time squared, or, length squared divided by time squared minus the same thing would be 0. Since we're doing dimensional analysis, we just know that they're the same. We're still talking apples there, so the units survive. And so again, this equation, pressure hydro or power hydro equals the time derivative of energy for hydro. And again, if you look at this guy, there's your 1/2 mv squared. That's energy. The one change is that little dot, and that's just the change in time that goes between energy and power. And it's something that we struggle with all the time, but right there is black and white. Energy and power are two different things, and that's how they're related by time. If you multiply power by time, then you get energy. Okay, so now I think these are things that we can deal with your system in a very concrete way and figure out how much theoretical power we're going to get out of this thing. Okay, now we're in great shape. So let's just do a little estimate as to how much power we think we might get going in. And in this case, the 1 is the same as velocity in. And maybe I'll just rewrite it here. So equals 1/2 m dot v in squared minus v out squared. So don't erase it. It's just another way of writing it. So, the 1 and 2 are arbitrary since back up in our system. Yeah, back in our system. I said, here's the in, here's the out. Where's 1? Well, 1 is in and 2 is out. Okay. All right. So, what we should be able to do on this m dot is know that m dot equals Q it's going to be Q times something. They're not the same thing. M dot is mass per unit time. Q is volume per unit time. How do we get between mass and volume in general? You guys remember physics class at all? How you get between mass and volume? What's the missing variable there? So think, cubic, well, gosh, what's a good example? A glass full of water obviously has more mass than a glass full of air. Why is that? How's the water different? I'm sure you can tell me, Justin, how the water is different from the air. I mean, this mug full of water is going to weigh more than the mug full of air. Why is that?
Because the water is more dense.
The water's more dense. There you go. So it's just density. It's just density. So if I multiply the volumetric flow rate, we'll be able to go and look that up. I mean, you can look up what the volumetric flow rate is of the Clark Fork River or whatever little stream you have, and that's going to be the maximum flow you could possibly get. I mean, we typically augment this by building dams. We don't have that option here, but if you were able to stick your barge out there and shove all of the water in the Clark Fork River, that would be the maximum power you would expect to get out of this thing. So if we know the density of water, we'll be able to get to our solution. So how could we estimate Q in this situation? I think we'll be able to nail this now. So we got because if you go online, it's not going to tell you kilograms per second. It's going to tell you cubic feet per second. So let's do it this way. Power.
Gallons, like 8.2 pounds.
Pounds, right? Yep.
Yeah.
So let's write it this way: 1/2 Q rho V in. And I think we'll be able to measure V in fairly accurately. And all I think we're going to need to do is pace off a length of the river, throw a stick in. Somebody else is down at the other end. Sit there with a stopwatch, and you'll be able to know how fast the river's flowing, right? So there's your V in. V out might be a little trickier, but I'm hoping we can come up with some little experiment where we can see what the velocity of the water coming out. Obviously, it should be less. If it was the same, if nothing was there, we wouldn't be able to harvest any power. But I think V in we'll be able to measure. So that's an experiment you should plan on doing next week. What's the velocity of the Clark Fork River minus V out squared, and I'll let you get creative on exactly how you measure that. But you see what I'm talking about. What's the velocity of the water coming out of your technology? Could you make that velocity be 0?
Velocity of the water coming out.
Yeah.
It's like a dam, more or less.
Yeah. So
You
could
just
you make
stopped
it? Could you make it be 0?
I could put enough friction that it didn't work.
Yeah. I mean, depending on how you design it, you might actually be able to get your. I mean, so obviously in your river, and I'll just do a little visual here. So in your river, the velocity is heading downstream, right? Now, and you'll have to just look at your design. This is something you consider. Don't change it up. But if you were able to make that velocity go sideways, essentially you've captured all of the velocity. You understand what I'm saying? So the velocity is moving in this direction. If you somehow kicked it back upstream,
Like an eddy?
you'd get even like an eddy. You'd get even more.
Okay.
And in fact, that's why some of the most effective power wheels, you might see water coming down and then splashing back up. If you're using a what's it called?
They actually make a whirlpool turbine. They use it a lot in Asia. That they make it come in so it hits the side of the water wheel. It basically comes into a bowl, so
Yeah.
they keep it just like your toilet. It
Yep.
keeps that swirl going.
And then ultimately, it probably heads
And then it just
down
falls
out of
out
that,
the
right?
bottom.
So it's same thing. Those two velocities are perpendicular. One's coming in this way. If it goes out that way, you've essentially captured all of that. So that's how to think about velocity in this thing. So we're going to have to get creative in terms of how we measure the velocity out. I think velocity in is going to be pretty simple, but if we can get that velocity out measurement, we'll know our theory dead on, because everything else we know. We know velocity in. We'll know, because we'll be able to measure that directly, and we're also going to know the mass flow rate. Well, I think we will. And here's how I suggest taking an estimate at that mass flow rate. So we can go online, we can see, all these are published. There's different flow meters in the rivers. So let's just take a look at the river right now. So Q, and we're looking like down the riverbed. So here's going to be Q, and I'll just say published. And right up the top of the river is going to be our little technology, right? Our little A. Right? So there it is, sitting right there. How can we then estimate the volumetric flow rate through our technology? We're going to go online, look up what the river's doing. What's a good way to estimate that? You got any ideas on that one, Austin? Like, I said already, if our technology, the entire river flowed through it, we know we'd capture all of it. So the the river itself, I'll just put this as a river. How might we then? So what we're looking for is Q micro hydro. So we know what the area. Let's put it down here. Micro hydro is. We'll estimate what the area of the river is. We'll get the depth. We'll measure the width.
And they give you a cubic feet per minute.
Yeah, exactly. And that's what we're working at is volumetric flow rate. So we're perfectly all set on that. So how might I arrange? So I've got these four variables. I've got the flow in the river. I've got the area of the river. I've got the area of our technology. This is the one variable that I need to estimate. Any ideas on that one? Okay. Well, here's how. I'm just going to set it up as a simple ratio, and say that the flow rate through the microhydro is going to equal, well, obviously the faster Q published is going, the more flow rate we're going to get, right? So think of a giant river with a whole bunch of flow. If that's bigger, it's going to be bigger through our technology too. If the area of the microhydro goes up, so will the flow rate through it. And the only variable of that I'm missing is just the area of the river. So this little guy here is just a fraction. And obviously we're only taking a fraction of the river, so maybe it's going to be 1/100th, maybe it's 1/1000th, but you'll know that number. And then, so you'll be able to measure your Q. That's going to be your volumetric flow rate that's going through your device. So now, for our power estimate, we're going to know what Q is. And again, this is the Q microhydro. We know what the density of water is. It's 1 kilogram per liter or 1,000 kilograms per cubic meter. We're going to be able to measure V in. I'm going to leave it up to you to get creative on how to measure V out. In a best case scenario, you could just sort of set this to 0. Let's just say somehow in the propeller you make, just like the one Tim was designing, if you could make all of that water just spray out to the side, you've essentially made it go to 0. It's never going to be perfect, but you can be close. So you could come up with an upper estimate at least as to what the power would be. Does that make sense? Mm-hmm. Okay. So let me write that out one more time. And this is going to be the final equation that I do want to see in your report. So I'll write it twice. Power hydro equals 1/2 the area of your microhydro over the area of the river times the density of water times your V in squared minus your V out squared. So that's the formula you're going to use for your theoretical maximum.
For density, you're talking the pressure?
Density, sorry. This funny looking symbol is actually the symbol rho. So when I was showing in Microsoft Word yesterday, if you type the letter R,
wasn't
yeah, no
here.
problem. Turn that into symbol, and from Times New Roman, that's an R. If I had a little, so it's not, that's a P with the little tail or head or leg or whatever you want to call that on the top. So, and again, this is going to be important in that list of symbols we talked about in report writing yesterday. So list all these guys out, and then we're good to go. You can also write it this: power, hydro, max. The max you could get is going to be 1/2 area micro hydro, and you'll have two separate ones. You'll have the area of your impeller, and then you also have the area of your paddle wheel, right? So you can do this twice for both different technologies. And then area of the river, we'll do our best at estimating that. We'll have the density of the water, H2O, and then we'll just assume that the V out is 0, and now our V in squared, and that's going to be the max if we were somehow able to take the velocity to 0. There we go.
If you guys doing on that irrigation canal, the easy way to do it, an easy way to get your feet per second or feet per minute for actual speed of the current is to go out and measure out, put out stakes 50 feet apart, put something in there, take, a water bottle or something that floats, put it at the 0 mark, use a stopwatch, let go, time it, and when it crosses the other line, that's how many seconds it took to go 50 feet. Now you can do your math to figure out how many feet per second that is, or...
Yeah. Oh, guys, sorry, I left one variable out. You should have caught me on that. I left out my Q pub, so I'll write it at the end here. So Q, and you would have noticed this, but that's the published CFS that you'll see on the, and I can show you the websites for that. So here's your Q. And then, so this is, so we've gone through the theory. You'll show that algebra, and then you'll be able to put the values in. And well, you want to just do one? Let's just do one quick little example. Let's do one quick little example. So equals 1/2. Let's just say our area. Let's just say we're capturing 1%. So 0.01. And then our density is 1 kilogram per, let's do it as a, no, let's do it the other way. Let's do 1,000 kilograms per cubic meter. And I don't know, what's a reasonable velocity? Maybe 2 meters per second?
That's probably pretty,
Yeah, so let's just go with 2 meters per second. And then what's a reasonable volumetric flow rate? Maybe we can just find
Right now it's like 2,700 cubic feet per second.
Is that right? Okay, that sounds about right. 2,700 feet cubed per second. And let's just turn that into cubic meters. I'll rely on the internet for that. I don't know cubic feet to cubic meters off the top of my head. Okay, so 0.028. So now we're looking at just lasso that, drag it over here, 2,700 cubic feet per second, and then we're looking at, go back, cubic meter. 1 cubic foot is 0.028, so 1 cubic foot is 0.028 meters cubed. Okay, so now we've got so let's see, we've got feet cubed are going to cancel. We've got meters cubed are going to cancel. We've got that area, we've got density, we've got kilograms still. Okay, and this is going to be meters squared, so let me pop that guy in. Okay, so now we've got mass, length squared, there's seconds in the basement squared. Okay, so now the units are correct. All we have to do is the arithmetic now to get the answer. So let me do that. Hopefully we'll come up with something. And here's where, in physics labs, you're like, 50 megawatts, probably not. 2 microwatts, probably not either. So the moment of truth is here. So 0.01 times 1,000 times 2 times 2 times 2,700 times 0.028 divided by 2 equals 1,500 watts. It's 2 horsepower, right? That's a pretty good ballpark. Now, that's if you're 100% efficient. And again, this is the max. This is the max you'd hope to get. What was the power on that little prop guy?
350 watts.
Yeah, so even smaller. And I think its area, and its area is probably more like 1,000th. So that's like taking it down yet another order of magnitude. So we're in the ballpark. And if you get 2 horsepower out of that thing, wow, probably going to be a lot less. But you'll go in and actually put the numbers in. We're in the right ballpark. Sound good?
You're going to figure your losses for your belts and pulleys.
Homemade pulleys.
Yeah.
You're gonna have your loss in your alternator,
Yeah.
heat, friction.
Yeah, we went over those thermal losses, little acoustic losses.
One thing I would recommend for you guys, because I know you're kind of at a crossroads here of most of the woodworking is done, so now you're looking at components and stuff. One of the things I would do is get some baseline numbers. That electric motor, the trolling motor, hook a meter up to it, spin it. Take a drill, it fits right on the shaft, and spin it. See what kind of numbers you get, see what kind of RPMs you have there. And use those numbers compared to how fast is it going to spin with all the pulleys, or how fast is it going to spin with that, theoretically, with that propeller. Now that you have these numbers, you should be able to figure out an RPM, or you should be able to design a blade to give you the desired RPM. And what is your desired RPM? It's probably about 1,600 to 1,800 RPMs on the propeller. I don't know exactly. You're going to have to figure that out. But you can get some baseline numbers right now with a drill that has a known, runs 1,250 RPMs at the top speed, and I get this many volts.
Yep.
So that gives me a starting point of, I can tell you right now, the drill will only spin it to about 9.1 volts. What do you need to charge a 12-volt battery? At least 12 volts,
Yeah.
right?
Drop out voltage.
So you're gonna have to add some numbers to that, so obviously, you're gonna have to spin it faster.
13.
So now's your time to play with that. I've also got a couple of DC motors set up over there, just little, like stepper motors. You can spin those and get
Yep.
an idea of how things work. Now's the time to do the research so that you can definitively say, yes, I can spin a car alternator and make enough power to charge this battery. Or I need a minimum of this many RPMs from this propeller to make the minimum 12 volts to be able to, and you do that through the pitch of the blades and the number of blades. So there's a lot of, you're getting into the engineering side of it now,
Yeah.
past the slap
Yeah.
stuff together.
Yeah. Yeah.
And then ideally, and at that point, I think you also need to start doing the shopping of, let's find an old car alternator.
Mm-hmm.
It has to work, but let's find an old car alternator, and ideally, maybe we can get it with the mounting brackets will make your life a little bit easier to, although we can weld something up if we need to. But now you're gonna start looking at, let's make those components, and how are we gonna capture what we just figured out here from the 2 horsepower we
Yeah.
can take out of the river? How are we gonna convert that to volts and watts?
Sound good? Okay, so that's pretty solid. I think you got your theory section locked in, and, now it's just a matter of, again, like Tim said, design a system so you can get as close to that max as you can, obviously make the thing work, and go from there. Okay, so,
And I've got that stuff set up on the back table with Wally, so I can walk you guys through it, just take a look at for like the boat, for the trolling motor.
yeah. And then I'll post that little video, and we can do it later, so.
Yeah, and you
Thanks a
said
lot.
that you were gonna post the one for how to do the reports and stuff.
Yeah, and that's already up there, in
So I'd
fact.
like to see
Yep,
that.
yeah, for sure.
Oh.
All right,
You were
team,
waiting,
thanks.
yes, thank you.